So in this video I want to discuss some stuff about homology classes of paths. So here, of course, we're considering paths. So these are maps U from the one simplex to X, where as usual we identify delta 1 with the unit interval 0, 1. 1 minus t comma t corresponds to t, right? So this is a point in the one simplex, and we identify it with t. So remember we had some constructions with paths. So we have a constant path, CA from delta 1 to x is just CA of T0, T1 is just equal to A for all points. Okay, that's and then so then if we've got a path U from delta 1 to x, we can reverse it, so in the original presentation, in terms of the unit interval, we would have said that U bar of t is U of 1 minus t. But the way, with this kind of identification of delta naught, the way it works out is just that you get U bar of T0, T1 is just a U of T1, T1, T0. We just swap the T0 and the T1 around. And then we consider the path join. Okay, so here we had a path U from A to B, and a path V from B to C. Then we want to define a joined path as a path going from A to C. So in this kind of new notation with the simplex, the way this works out is as follows. Okay, so the condition before was that t should be between you split it depending on whether t is less than or equal to a half or greater than or equal to a half. But if t is less than or equal to a half, then that means that 1 minus t is bigger than t. And if t is bigger than a half, that means that 1 minus t is less than t. So the correct way to split here, well, is the sort of first part is where t0 is bigger than t1, and the second part is where t0 is less than or equal to t1. And in this case, we've got our u, and it turns out that, the right thing to do here is you've got t0 minus t1, 2t1. Okay, so it's basically the doubling of speed comes into giving this factor t here, and then to make the sum of the two entries be equal to 1, which it has to be for the simplex, you have to say subtract off the t1 from there. And that's okay, because t0 is bigger than t1, so t0 minus t1, that's positive. And so this really is a point in the one simplex, and that's how it works. And then kind of symmetrically, the way it works here, you get 2t0 and t1 minus t0. So let's just kind of check this is working properly. So if we look at the starting point of E0, that's 1, 0. Okay, so that's certainly in the case where T0 is bigger than T1. So we get a U of your T0 is 1. You got T0 minus T1 is 1 minus 0, and 2 times 0. In other words, that's U1, 0, which is A, and U star V of 0, 1. Okay, so now we're certainly in the range where T1 is bigger than T0, so we're using the second clause here, and so we get a V, and this first thing is twice T0 is 2 times 0, and the second thing is 1 minus 0. So V is V of 0, 1, Okay, that's the end point of V, but V was a path to C, so that's equal to C. And U star V of the midpoint, half a half. Okay, so using either of these things here, you're going to get U01, which is B, or V10, which is also B. Okay, so it all fits together. This is the correct way to express the path join and the path reversal operations and constant paths in terms of the one simplex instead of the unit interval. So now we want to describe how these path operations interact with homology. Okay, so firstly, the claim is that for any constant path lies in B1x, the group of boundaries. The thing that remember, H1x was the quotient group Z1x mod B1x. So so this we can rephrase, if you like, as saying that this coset. So we look in the quotient group, then this constant path represents the trivial element. And then for any u from delta 1 to any path like this, well, u plus u bar is in B1x. In other words, u plus B1x is the negative of u bar plus B1x. So notice here, I mean, u is probably not in Z1x here. So we can't think of this as being an equation. You can't, strictly speaking, think of it as an equation in homology, because because if u is not in Z1x, then this you don't get an element of the homology group. But still, we can work instead in this quotient group here, where we take the whole of C1x mod B1x, and we say that these two cosets are the same then. And then again, we've got a relation, a homological relation for the path join operation. We look at we take u star v, so that was a path that we said from A to C, and we look at the coset of that. That's the sum of the cosets of u and v. Okay. So kind of if we're working kind of homologically, modulo boundaries, then the path join operation is kind of the same as the sum operation. So that's what we need to prove. So the first thing, okay, so CA here, I mean, CA is a constant map from delta 1 to x, and let's write C prime A from delta 2 to x be constant. With value A, okay, then and if you compose that with delta naught or with delta 1 or with delta 2, those are all you compose a constant map with an inclusion that's still constant, still same value. Okay, so these things are all equal to CA. So that means that if we take the boundary of C prime A, we get CA minus CA plus CA, which is CA, and that means that CA is in the group of boundaries. Right? CA is D of something, and B, it's in the image of D, which is by definition equal to B1x. Okay? So that proves our first claim. Okay, now for the second claim, say okay, let's suppose that U is a path from A to B in X, and then the claim was that U plus U bar is in B1X. And to prove that, well, let's define, let's say, M from delta 2 to X. So M of a typical point T0, T1, T2 is going to be U of T0 plus T2, T1. Okay, this is valid, right? Because this T0, T1, T2 we're assuming is a point in delta 2. Okay, so these T0, T1, T2 they're all non-negative, and the sum of them is equal to 1, and therefore T0 plus T2, T1 they're both non-negative with sum equal to 1. This is a point in delta 1, and so we can legitimately apply U to it. Okay, so then we want to understand what's dm. So we look at m delta 0 of T0, T1. Okay, so that's m of 0, T0, T1. So that's U. Okay, so what do we do? So here we take the sum of the first and last coordinates. So we take the sum 0 plus T1, T0. In other words, U, T1, T0, which is U bar of T0, T1. Okay, so yeah, the M delta 0 is the same as U bar. And we do M delta 1 of T0, T1. Okay, so that's M of T0, 0, T1. Okay, so that's U of, again, you take, here the rule is we take the sum of the first and the last entries, which is T0 plus T1. Okay, but this T0, T1, that was supposed to be a point in delta 1, which means that the sum of the two coordinates is equal to 1. So this is just U10. Okay, or U of the basis vector E0, which is the starting point of the path U. And U is the path from A to B, so this is just equal to the point A. Okay, so M delta 1 is the constant path with value A. And then if we do M delta 2, okay, so that's the same as M T0, T1, 0. Okay, and then again, the rule is you take the sum of the first and the last entries here, which is T0 plus 0, which is T0, and then you take your T1. So what do we see here? M delta 0 is U bar. M delta 1 is the constant map CA. M delta 2 is U. So we get that dm is U bar minus CA plus U. So in particular, you get U bar plus U minus CA is in B1X. Because this is just equal to dm, and B1X is the image of D. But also, we had CA was in B1X. That was by part 1 of the claim we're just proving. So we find that U bar plus U is in B1X, as was claimed. Okay. So now we've proved the first two parts of our proposition. The part about constant paths and reverse paths. Now we just need to do the thing about path join. Okay, so for the path join, let's suppose again we've got path U from A to B and a path V from B to C. Okay. And we need to produce a suitable map from the 2 simplex delta 2 into X. So let's just kind of draw a little picture of how this is going to work. Right? You've got your E0 here and your E1 here and your E2 here. And we're going to kind of split this triangle into 2 parts like this. And our U is going to go along here, and then up here, just on this half here, that's going to be a U as well. Whereas along this edge, we're going to do V, and then also along this kind of half edge, we're also going to do V. So this edge of the triangle is like U star V, and then this edge is U, and this edge is V. Right? And the formal definition of it P from by P of T0, T1, T2. Okay, so notice that this so this is kind of going. This is like 1, 0, 0. This is 0, 0, 1. This is where T0 is equal to 1. This is where T0 is equal to 2, and this line in the middle is where T0 and T2 are the same. Okay, so the distinction we need to make is between whether T0 is greater than or equal to T2. That's going to be this bottom half, or where T0 less than or equal to T2 is the top half. And where it works, yeah. So here we in this part we're going to do U, and we want T0 minus T2, T1, and then 2T2. Okay. And then kind of symmetrically here, in this region you're going to have 2T0, T1, and T2 minus T0. So notice this kind of makes sense. Because T0 is bigger than T2, this thing is positive, and those two are definitely positive. And then you add these 3 up, then you're going to get T0 plus T1 plus T2, which is equal to 1. So this really is a point in... no, I said this wrong. Yeah, this is supposed to be T1 plus 2T2, and then here, this is 2T0 plus T1. Okay, so these are supposed to be points in the 1 simplex. Okay, so they've got 2 coordinates, right? And so this coordinate here is T0 minus 2T2. This one is T1 plus 2T2. Both non-negative, and you add them up, you get 1. Okay, so this is meaningful, and we need to check consistency. Okay, you need to check that these 2 clauses are consistent when they both apply. So if we look when T0 equals T2, first clause gives so here T0 and T2 are the same, so this guy is 0, and then everything adds up to 1, so that has to be equal to 1. So that's the U of 0, 1, that's the end point of U, which is B. And the second clause that gives us a V, okay, and again, so the second coordinate, T2 minus T0, because T0 and T2 are the same, so that's going to be a 0 in the second coordinate, and everything adds up to 1, so you have to have a 1 in the first coordinate. So that's the beginning point of V, which is also equal to B. Okay, so the 2 clauses are consistent when they both apply. So this is a well-defined continuous map from delta 2, and so let's look at the boundary of this P. So we do P delta naught of T0, T1. Okay, so that's P of 0, T0, T1. Okay, so here the 0 coordinate, this is the 0 coordinate, the first coordinate is less than or equal to the last coordinate. So we're in this second clause here, V, and in the And so here you get twice the first coordinate plus the second one, so that's 2 zeros plus a t0, which is t0. And then here you get the last coordinate minus the first one, so that's your t1 minus 0, which is t1. Okay, so p delta naught is v. And if we do, let's do p delta 2 next. Okay, so so that would be t0, t1, 0. Okay, so we're in the situation where the the first coordinate is bigger than the last one, so it's this first clause here. So we get a u, and so here we get the first coordinate minus the last one, which is t0, and then you get the middle coordinate plus twice the last one, which is t1. So p delta 2 is u. So now let's look at p delta 1 of t0, t1. So that's p of t0, 0, t1. Okay, so again, we have to split according to whether the first coordinate, according to the first coordinate and the last coordinate, their order. So the first situation is where t0 is bigger than or equal to t1, or t0 less than or equal to t1. And so in this first situation, then you get you get u, and you get your t0 minus t2, so this is like the first coordinate minus the last one, which here is t0 minus t1. And then here you get the middle coordinate plus twice the last one, but the middle coordinate is 0, so that's just 2t1. And then here, similarly, you're going to get v of 2t0, t1 minus t0. Okay, so here we're seeing this is the same as u star v of t0, t1. Okay, so putting this together, we see that dp is u minus u star v plus v. Therefore, u plus v is equal to u star v mod b1x. Because difference between the two sides here is equal to dp, so it's a boundary, it lies in the b1 group.